everybody. This is Yeshwanth Vijayakumar. I'm a senior engineering manager at Adobe. I work with the Adobe Experience platform, specifically for the unified profile tool. Today, I'm here to talk about how Adobe uses Spark structured streaming at scale. Today's agenda-wise, we're going to go through a bunch of topics, mainly, as in we'll start with ingestion-related topics, and we'll slowly step into how we optimize our code, as well as applications like streaming statistics, etc. The main takeaway that I want you guys to have from today's talk is that hopefully it saves at least an hour of your time when you're trying to solve similar problems. So yeah, let's get started. First, we need to understand what kind of architecture are we dealing with. The unified profile specifically is at the heart of the Adobe Experience platform. The entire product exists to make sure that a customer can get a 360-degree view of their users. We have a lot of marketing information flowing in from internal solutions like Adobe Campaign, which is like an email campaign optimizing tool, and also things like AEM for website building, and also Adobe Analytics, which is one of the largest analytics vendors out there, and solutions like Advertisement Cloud, which lets you optimize advertisement campaigns. So the data can come in as part of JSON, or can come as Parquet, or can come as protobuf, or any format that is kind of imaginable under today's ecosystems. All of these different formats get converted into the experience data model. It's our own version of standardized marketing in JSON that is useful for targeting purposes, building models, exporting, segmentation, etc. At the heart of our operations is Apache Spark. We use a lot of Apache Spark in our ingestion, in our processing, export layer, almost everywhere that you can imagine. And then the data makes it into unified profile. The unified profile itself is like a single tenant solution, meaning every single client has their own instance of the unified profile. All of the changes that come into the unified profile also feed into the change feed. So this fire hose has every single logical change that has been committed into the tenant's unified profile. Using this fire hose, we're able to do a lot of operations, like the statistics generation and the streaming fashion, etc., and a lot of other production use cases that we can think of. When we talk about structured streaming, right, the first thing that we want to understand is what is the lag. Like having a streaming-based ingestion mechanism always makes it very, very hard to track how much progress we have made. Thankfully, Spark has made it easy, as in they have some asynchronous APIs that we can register, like the streaming query listener, which we can extend and create our own listener. It exposes a very useful function called the on-query progress. So this gets triggered every time a successful MicroBatch for Spark structured streaming ends. What we have at hand when we define our own on-query progress is metrics like the number of input rows that have come inside for each microbatch, also the input rows per second, and also the process rows per second. All this comes in at the end of successful batch completion. There are other bindings also that you can utilize, like the on-query started or the on-query terminated. But for the focus of this talk, we're just going to focus on the on-query progress because we want to report on successful metrics. And these can be piped into Prometheus or any other metric monitoring system that you want to. But this just solves the problem of, okay, how much progress have we made, right? But usually, when we are consuming off of like a firehose, say, like of Kafka, like the change feed example that I gave before, what we want to know is how much have we done, or how much have we successfully processed compared to how many records are there, what to say, at the queue itself. So for that, we have what we do is we put in a very interesting hack, because Spark streaming, every single time you start a new uh, a streaming query, it creates a new version of the consumer group. So which makes it extremely hard for us to track. This has changed in the recent versions of Spark. But when we started out, we were stuck with the fact that, okay, every time we started a structured streaming query, we had a random consumer group and we could not track that. Now, what we did to get over that is that we created our own dummy consumer group, and we created and passed that to what we call as the Kafka lag writer object. Now this basically extends the same streaming query processor, but what we do differently is that we commit the offsets of whatever progress we have done so far into this dummy consumer group. This idea came from this wonderful blog that I have linked over here, and this has actually made our lives very easy. Now you might ask, okay, why do you want, what are you going to get with the dummy consumer group per se? So what happens is we're able to use Kafka's Burrow, which is like a monitoring companion that comes with Kafka. So we are able to track the lag of that dummy consumer group now, instead of trying to hunt which consumer group got created by the structured streaming query. So we know exactly how much lag or how much more work do we need to do to keep up with the traffic or throughput on the topics. So one example that you can see here, like we're almost crossing 3.5 million records per second at peak. So all these things get, what to say, are like a side effect of the streaming query listeners extensions that we have put in place. The main reason we are doing all this is because if we don't measure how well we are doing, there's not much we can optimize for. So now that we have put all these measures in place, we can look into how we're actually optimizing the ingestion path, that is getting the records in. The generic flow, like if you look at Spark structured streaming, right? So you have a Kafka topic, say you have 2 partitions, and now what happens is, say you have 3 executors now. What will happen is, and you have some business logic on running on each of these executors, and then that gets written, whatever records get processed by these executors with the business logic, they get written to a sink. Now, this is like a very generic flow. Right? Now, we need to look at, from the code point of view, how can we optimize this flow? Here we have an example where we have loaded in a Kafka stream inside, as in for the structured streaming query. And what we're going to see is that you can see the example, like we're using .format as Kafka, and we have a bunch of different options that are specified here. What is this going to mean? So in order to optimize, our read flow, right, what we need to do first is keep our executor resources constant. If we keep changing the number of executors on every single experiment that we do, it's going to be extremely hard for us to figure out proper parameters that we get optimized. The first and most important parameter that I feel is the max offsets per trigger exposed by the Kafka connector structured streaming. What this says is how many offsets should I get from a Kafka topic or a bunch of Kafka topics for every microbatch. What the microbatch is in, and the microbatch interval is specified by the trigger interval for a given structured streaming query. So in our use cases, we usually use a 30-second trigger interval. So if this is set to say 100,000, what that means is across all the topics that we are subscribing to, we are asking the structured streaming orchestrator to fetch 100,000 offsets from across these various topics uh, to be loaded into our context so that we can process them across the 8 different executors. So this will determine what QPS that we want to hit. So if you want to hit, say, 1,000 records per second, and if you have a trigger interval of, say, 30 seconds, it means that you need to have at least 30,000 offsets per trigger specified in this setting. So this goes a long way in, what to say, being like, what is the hypothetical QPS that you need, notwithstanding any code changes or any other optimizations we need. The next important thing is we need to make sure that the processing time is less than equal to the trigger interval. So like I said, trigger interval of 30 seconds means every 30 seconds, Spark is going to trigger off a MicroBatch to pull in records from Kafka, from the bunch of topics that we're subscribing to, and send them over for processing. Now, say if the processing time for this MicroBatch is 40 seconds, that means by the time, what to say, the actual processing is finished for that MicroBatch, you should have already started the next trigger interval, but Spark cannot start it because you're already 10 seconds behind. So you're always going to be trying to catch up, which is kind of a bad thing in this place, specifically in the streaming one. So what we want to make sure is the processing time should be well within the trigger interval bounds so that you have a good amount of headroom to grow like queries per second. Yes. The next and super important parameter, and this is extremely important from the optimization point of view, is the MinPartitions. This is not that well publicized, but we will actually go a bit deeper into why this makes a big difference. What MinPartitions does is it enables a fan-out pattern. So every Kafka partition gets mapped to multiple subpartitions on the Spark side. What does this mean? We will look at that in the next few slides. So, but before that, right, we need to rinse and repeat this process and keep modifying these parameters. As in assuming you have some excellent code written and you don't need a lot of optimization there, right? This is as you've already put it through JProfiler, etc., to make sure your code is actually pretty good to execute. Now, diving deeper into the min partitions thing, right? What happens is if you have, say, 2 partitions on the Kafka side, and say you specify min partitions equal to 6. Now, Spark will divide it, will basically divide the partitions to go to multiple sub-partitions on the executor side. So partition 1 can, go into partition 1.1, 1.2, and 1.3 across executor 1 and 2. Now, this has a lot of hidden advantages, right? Most of the time, one common thing before I knew this could be done, I was like, hey, you know what? I think we're bound by throughput, as in our throughput is bound by our Kafka partitions, and that was my initial assumption. And then I would raise a request to the Kafka pipeline team to say like, hey guys, can you increase the number of partitions? They'd be like, why can't you just do a fan out? And I was like, oh, let's look more into that. Thing is, you don't want to keep changing your infrastructural bounds to map your computational bounds. So you can get a good amount of data pumping in, and then you can feed your computational needs very well with the min partitions parameter. The next thing that we want to look at is actually the logic part, right? How we express our logic goes a long way in determining how well our throughput will be. So we're going to compare 2 common paradigms of expressing the logic in Spark. This applies both to batch and streaming. So we will look at it from either way. So from the map and for each, the map or for each paradigm that is there, right? You're looking at record by record processing. So if you look at the example there, it's like the data set dot filter, you're seeing filtering all the records that have a signal parameter greater than 10, and then you're doing a map on each record that matches that filter criteria, and just emitting out the device aspect of it. You could do a similar thing on the for each side too. The main key thing is you're operating record by record. What are the advantages of this, right? This is extremely easy to code. You don't have a lot of thinking to do with respect to the visualization aspect of it, because you're just doing record by record. What are the problems, right? This is extremely slow. We can't do any local applications unless you decide to go pro and you create your own explicit combiner, which Spark can utilize. And the cost of this simplicity is Spark has to spin up a huge amount of individual tasks to take care of this. This is not going to be a problem in most of the applications, right? Specifically, when you're optimizing for throughput, this becomes a big deal. The next big thing is, say you are writing to an external sink. Connection management becomes extremely important in this use case. So if you look at the structure of the code itself, managing connections in this row by row approach is going to be extremely hard. Now, directly contrasting with the map partition or the for each batch use cases, right? So in this case, we are operating on a batch of records. So every partition, every Spark partition gets a task, and we're going to operate on top of that. In this, we can do explicit connection management because we are operating, as in for every group of records, we can start and stop the connection. So with respect to batching and reuse, this is extremely good. We can do local aggregations using simple things like hash maps. We don't need to rely on complex signatures like combiners. Instead, you have a very simple hash map based aggregation that you could do. But cons wise, you can't just blindly take the map paradigm logic and then write it into map partitions and expect it to have an immediate effect without accounting for memory as such, memory and CPU. Because earlier, your tasks are configured for single row by row processing. And then now you're doing groups of rows. So your tasks need to have a bit more firepower. So simple things like, Spark or task of CPU is equal to 2, or adding more memory to your tasks. That is a simple mitigation strategy you need to try. The other big thing is visualizing all of this is not exactly straightforward. So if we take an example, right? So this is a not so simple example where we are in the for each batch, we are actually creating some bloom filters, and we're going to write it to Redis. So in this case, you can see that within the for each batch, when it starts up, we create a Redis connection. And then we're able to do some local aggregations by using the data frame itself, as in the batch data frame object that we get from within the for each batch. So here we're able to get the distinct products in every MicroBatch that we've gotten. And here we use the Redis connection to perform individual operations on top of that MicroBatch. And then once all the batch work is done, we close this up. How this would look like in a map would be extremely similar. Actually, not extremely similar. We will set up a connection and we will direct it in. But then the connection management is one, you do it on a row by row basis. That's one problem. The other one is the aggregation wise, you would need to split this across multiple stages in order to do the aggregation. So a lot more shuffling, and it's just going to make your process way more slow. But of course, your mileage may vary based on what your logic is. If your logic is not that complicated, I would stick with the map and for each. The other important feature from Spark, which applies to the structure streaming part, is Spark speculation. Speculative execution. This is nothing new for those of you coming from the Hadoop map reduce land, right? So if Speculation is set to true. What it means is in a given stage, if there are some tasks running extremely slow compared to the rest of the task execution, Spark will automatically launch duplicate tasks and basically pick the result of whichever task completes first. So one interesting parameter to control, from runaway speculation in this is the speculation quantile. So if I set a speculation quantile as 0.9, it means that at least 90% of the tasks in that stage need to be complete before the speculative execution duplicate tasks get started. So this has been a huge game changer for us because you can see here, like this tries to maintain the average timings on an every microbatch basis um, by spinning up new additional tasks and killing them off. And this aggressive speculation is what helps us maintain our throughput. Some caveats though, you need to be aware your logic, that is your writer logic, the sync logic needs to be aware of um, the idempotency in play. If you are not, if your logic is not idempotent, you will end up with wrong results. Like if you're doing a plus or a minus operation within your sinks, if multiple sinks, if duplicate sync tasks run, you could have double counting or triple counting kind of cases. If you're doing unioning, in that case, you get away with a lot of things. So that caveat has to be kept in mind. Now, getting to the streaming statistics calculation, this is a very common use case, right? Like one of the main reasons is Spark has amazing windowing functions. So we want to look at what kind of pitfalls can we have during the aggregation process. So let's take an example, right? We saw a similar thing before, like loading a Kafka topic into a Spark structured stream. So we have an events data frame. It's basically has all the events data loaded into it, and as in the incoming data, it's hooked on to the incoming data from the Kafka topic. So we have two different scenarios here, right? So a simple thing can be like, hey, I want the event count by half. So we do a group by event type, and the windowing thing tells us like every hour I want to bucketize this stream by every hour, and I want the count of the event types over here. And we can take an almost duplicate case where it's like I want the product count by half. So tell me which products have been purchased and for that hour, and I want to know the distribution of the product IDs for them. So they look extremely similar, but then there's a lot of difference between each of these. So if you look at the intermediate state store that Spark structured streaming maintains for this, it would look something like this, like between 8 p.m. to 9 p.m. For purchases, you have 500 items that were done. You had 5,000 add to carts done, and between 9 to 10, again, you had 70 add to carts. Now, if you look at the result table for the second query, right? Now, this is going to look similar, but completely different in terms of cardinality. The first one is extremely low cardinality because the number of event types that you have is very small, finite. But the number of products, on the other hand, they're extremely large. You could have, say, 100,000 products. Now, if you're going to cross it with every hour, with the hour dimension, it's going to be very difficult to keep track of it in the state store. But why should it be difficult to keep track of it in the state store, right? So by default, it is stored in memory, that is, it's managed by the JVM. A large number of keys, like you saw in the second case, means that you will have frequent GC pauses. You have more frequent GC pauses, you're going to have higher latencies because your microbatch timing is going to increase, and then your lag is going to increase. So you're going to be in this catch-up state forever. One way to get around this is to switch to an off-heap state store. So one example is using the RocksDB state provider. This is available, in proprietary in the Databricks distribution. But then there are a lot of open source versions of the state store too. So the advantage of the off-heap state store is you can manage way more keys safely. Say, I would easily put it like as 100-time difference, right? If you can store 100 keys in memory safely, as long as you have a good SSDs going by in your infrastructure, you can easily get say 100,000 keys stored and also have a good access pattern with respect to that. Another thing is you can also implement your own off-heap state store. Like sometimes people might say, hey, you know what? I want to use Redis. I don't want to use rocks. I want to use LevelDB instead. I want to use something else. I can, why don't I use DynamoDB to store my state? So Spark actually does make it pretty easy. So you could extend your own state store provider and set it in your Spark configuration and you're good to go. So it's extremely important. This is probably one of the biggest for performance differences that you will see as you're trying to get into higher throughput loads and also are doing more complex calculations, aggregations on the streaming workflows. Another thing that I would also like to mention is you want to try to keep your windows shorter. You don't want to have very wide windows. In that case, the amount of you're not going to be able to discard the data. If you have say a 7-day window, it's more work for the state store to hold on to. The other big thing is Skew. So what happens is, so in Spark, say if you have say 9,997 tasks complete out of 10K tasks, it doesn't matter, right? If 3 fail, your entire stage fails. So you need to retry the whole stage. So the problem is, like, as you are getting data through from multiple partitions, the distribution of the data across those partitions might not be ideal for processing. So you might end up having too much data in one of them, causing out of memory or like connection failures. So this can lead to a lot of cascading effects. So repartitioning is your friend for the time being. So you pick a column which you want to repartition, and then you're good to go. But the thing is, it's in practice though, it's not enough per se. So what we want to do is we want to uniformly distribute the data. So the column that you are using might not have a uniform distribution. So instead, what you want to do is you want to add some salt to actually make it uniformly distributed. So the transformed column becomes a salt key for each row, and then that makes it much more uniformly distributed. So a lot of the time, what happens is, if you look at this example, we are specifying a magic number called the target partition count. So sometimes, depending on application, you might already know what that magic number is. Other times, you want to probably have a database way to figure that out. So some of the things that we use, right, to determine that is we were trying to mimic the HTML block size, which is 120 MB. So we wanted to make sure that the size of the partitions that we write is close to 120 MB. So what you can do is you can sample a small portion of your data that's already streaming in or that's already come inside, and then try to just take a sample out of that. Even a df.head is probably okay, as long as you're taking various df.heads across some periods of time. So you can estimate the size of each row, and then you try to extrapolate the number of partition counts that you actually want. So this is going to be helpful in both, batch and streaming use cases. In streaming use cases, though, one thing to keep in mind is this might not be enough, and you might need to do a second level of compaction after the fact that you write the data to an intermediate place. So for the estimate partition count, we have used the get size in bytes to try to get a rough estimate of how big each row is. And then we try to extrapolate how many rows would it take to fill one partition? Another optimization that I want to end with is Redis. So in our use cases, we use Redis as a sink to store a lot of the streaming statistics that we create. So Redis by itself is really, really fast. But then when you're writing from Spark and bursty traffic, you could end up overwhelming it. So one thing to do is you want to avoid creating too many connections. But the thing is, remember we spoke about for each batch, right? So we already have a kind of a construct where we're batching together multiple records. So one thing to keep in mind is Redis pipelining. So without pipelining, what happens is the client sends a request, server sends an ACK back, and then the client sends it again, the server acts back. With pipelining, though, what happens is the client sends a bunch of requests saying like A, B, C, and D, hey, do this, do that, and so on. The server gets a bunch of them together. So it's kind of like a MicroBatch on the server side. And then it returns a bunch of responses back in one shot. So this is extremely useful in Redis, where we see a huge boost in the throughput that we're trying to write to Redis. And specifically from the Spark side, when you're trying to write to Redis for a good burst of traffic, this becomes extremely useful. So let's take a similar for each batch example that we took, right? So how do we enable pipelining from Spark into Redis or in Gem 20, right? So what you want to do is set up a common connection for each batch. And before you start doing anything else, right, you want to set the auto flush to false, because you don't want the commands to be flushed so that they get sent to the Redis server immediately. You want to buffer a good amount of calls before you actually send it out. The next thing is you do all the processing that you want to do, like you group them by, say, specify a group size of 10 or whatever, depending upon what load your Redis server can take. And then you do a bunch of operations, like in this case, we just adding a bunch of elements to a set. And then when your group is complete, that is, you've finished loading your buffer, it's locked and loaded, you flush it explicitly. Now that you've flushed it, now the commands get sent, you wait for the act to come back saying that Redis has acted and the work is done, and then your Redis connection can be closed safely. So these are all the optimizations or tips, tricks, however you want to classify it, that I want to share with respect to how we use structured streaming and Spark in general. Any questions and comments are definitely welcome at these locations. So thank you for the opportunity.